Hello, welcome to Unit 7. This is the first video of Unit 7, and we're just going to do a quick little recap. This isn't like a full-on lesson to start, and then we're going to get into what the actual lesson begins with. But we are going to be working a lot with radicals in this unit, so you have to remember how to simplify them. There's a couple of different ways to look at it. Excuse me. So the first question is, what is a square root? What does it mean to take the square root of a number? So what we're doing is we're looking for a number, when you multiply it by itself, gets you to the desired number. So in this case, if you look at the square root of 49, we know that the square root of 49 is 7. It's a perfect square because 7 times 7 equals 49. A number times itself gets you to said number. So when we're simplifying radicals, sometimes we don't always have perfect squares, but we can represent them in ways that are equivalent. So 60, if you recall, you can break that up into 2 times 30. So we do this factor tree method a lot. I'm sure a lot of you are comfortable with that. And then 30 breaks into 2 times 15, and 15 breaks into 3 and 5. Now, we're taking the square root, so we're looking for groups of 2 that are the same number. So in this case, we have a pair of 2's, but 3 and 5, they don't belong. Sometimes I like to box them because they're actually going to stay underneath the radical. So this pair of 2's is going to come out as a single 2, and then 3 and 5 are left inside, but we have to multiply them. So if you look here, that's exactly what we get, is 2 square root of 15, because 3 times 5 is 15. So same thing with 200. If you think of this as 2 times 100, now 100 should be jumping out to you because that's a perfect square. So that breaks up into 10 and 10. And once you get the same number paired up like that, you can just pull it straight out. So we would have 10, and then we have this lonely little 2 left over here. So method 1 is the prime factorization, like I was just talking about, where you do the factor tree. So this would break up 7 and 9, and then 9 breaks up into 3 and 3. So we circle the 3's because they come outside. We have a pair of them. And then we have the 7 that stays inside. So this is one way to do it. And then the method 2 is to look for perfect square factors. So it's to recognize the fact that 9 times 7, 9 being a perfect square, so right away you can just take the square root of 9. We know that's 3. And then 7 doesn't have a square root factor, so we leave it as 7. And there we go. But notice we get the same answer both times. Now, rationalizing the denominator, this is something you've definitely seen before. It's probably just been a while. You look at whatever your denominator is, and you multiply the top and the bottom by the radical in the denominator. So in this case, we would take the top times the square root of 3 and the bottom times the square root of 3. What this does is 1 times the square root of 3 is just the square root of 3, and then the bottom, you can actually multiply 3 times 3 under the radical, and you get the square root of 9. Now, the square root of 9 simplifies to be 3 because it's a perfect square. So this would be the rationalized version. Same thing with 1 times the square root of 2. Take it times the square root of 2 over the square root of 2. You get the square root of 2 over the square root of 4, which equals the square root of 2 over 2, because the square root of 4 becomes this 2. Now, you can just skip that step. You don't have to worry about doing that every single time. I'm just showing you where it comes from. So this one, if we wanted to rationalize it, we would multiply by the square root of 5 over the square root of 5. So the top, you cannot multiply the 2 and the 5, so we just put them side by side. If one's a radical and the other isn't, then you just have to put them together like that. Now the bottom, though, since they're both radicals, you could multiply, and we know that it would ultimately just become 5. And that would be the simplified radical answer. Okay, so we're just going to continue on. I think you guys get that process. The real lesson for today is about the Pythagorean theorem. Very important theorem in geometry. We use it a lot. And this unit is about right triangles, so this is definitely something we got to be considerate of. So the definition of the Pythagorean theorem, it's in a right triangle, the square of the hypotenuse is equal to the sum of the squares of the legs. So the two smaller pieces of a right triangle, when squared, have to add up to make the squared version of the hypotenuse. Okay. Excuse me. Now, another phrase that you might have heard before, maybe not, is what's called the Pythagorean triple. You've definitely seen these before. And it's when you have three integers known as A, B, and C, whose values can form the sides of a right triangle. So basically it's three whole numbers, is usually what they are, that end up being, they fit perfectly in a right triangle. There aren't any decimals, there aren't any radicals that we have to worry about, because oftentimes when we take the square root to solve, we get decimals and radical answers. But in this case, the most common one is the 3, 4, 5. Some other popular ones are 5, 12, 13, and 8, 15, 17. Or we can think of any multiple of these groups. So the last line here, I want you to think of 6, 8, and 10. These two actually relate back to each other. It's just if you take the top, 3, 4, and 5, multiply it by 2, you get 6, 8, and 10. It's because those triangles would be proportional because they have a scale factor of 2. Their angles would be the same, and their sides would be proportional. So that's why we can adjust it in that way. Okay, continuing on. So we can actually find the value of x using the Pythagorean theorem or Pythagorean triples. So we'll start by using the Pythagorean theorem because that's what we've... and the Pythagorean triples idea doesn't always work. It's only for specific triangles. I should mention that right away. Now, the Pythagorean theorem, as we know, a squared plus b squared equals c squared. You just have to decide what are your a, b, and c, and then you can fill in. So in this case, c is the most important one, and that's the hypotenuse, which is going to be x because it's across from the right angle. So I'm going to say that this is my a, this is my b, so I'm going to get 45 squared plus 24 squared. And again, you can go either order with a and b. I could have chosen 24 to be a and 45 to be my b. So 45 squared is going to be 2025. 24 squared is 576. And then x squared. And then we need to add these two first, which gives us 2601. And then we just take the square root of both sides, and we would get 51 equals x. Now the fact that I got all nice numbers, 24, 45, and 51, guarantees that this is actually a Pythagorean triple. So if you look at the other two here, if you looked at just 45 and 24, and you thought about one of these groupings up here, 45 and 24 are both factors or multiples of 3. And it would be 3 times 15 and 3 times 8. And 8 and 15 are part of that Pythagorean triple, this one right here. So we know that the last one would also have to be a multiple of 3 times the last number is 17, and 3 times 17 does give us 51. So if you recognize that it's a Pythagorean triple, you can go ahead and identify that and fill in those pieces, but it's not something that works every time. We're going to get a lot of decimals, a lot of radicals, but it's nice to know too. Okay. I'll do this one as well. So just an application problem with the Pythagorean theorem, since we don't always end up doing those. You can actually calculate the area of a right triangle here. Well, technically the whole picture isn't a right triangle, but we can break it up into 2 right triangles. So notice this here is our missing side. This is the height of the triangle, which we need to find the area, because area equals 1/2 base times height. Now we have the base is 28, h is what we need to solve for. Since 28 is this whole distance here, we can recognize that this bottom piece is just going to be 14. And then we also have the longest side of our right triangle, which is 50. So we can set up the Pythagorean theorem as a squared plus 14 squared equals 50 squared. This time we have to recognize that we already have the c value. and we're solving for the height, which we're going to say is a. A squared plus 196 equals 2,500. And we're going to subtract 196. We're going to get a squared equals 2,304. And then we're going to have to take the square root of that. Use my good old calculator here. And we get 48. Oop, sorry. Okay, so a squared, or a, because we already solved for that, a equals 48. Now that is our missing piece. That's the height. So now what we got to do is to take 1/2. The base we know is 28. We just solved for the height. That's our 48. We can just type those in our calculator. 1 divided by 2 times 28 times 48 gives us 672. And that would be feet squared. So you just need to be prepared to apply the Pythagorean theorem as well, because there's definitely plenty of applications. It's one of the most important theorems just like ever discovered in math. We use it in so many different things. So, but that is it. Make sure you do the notes and then do the first lesson on, or the first homework titled Pythagorean Theorems, Unit 7.